Hello, guys. Welcome to today's stream. So, okay. So, please, if you can hear me, please drop a comment in the in the comment section. So, um, would be like a little bit late today. So, we'll start by 8:10, and hopefully we'll be able to wrap up everything before um be able to wrap up everything before 9 o'clock. So, in an hour, we'll be able to wrap up everything. Please, if you can hear me, drop a comment in the comments. All right, thank you. Thank you. So, I will just go ahead and start start this. So, the topic of today's stream is something I just came across, right? And is basically queues. Is a DSA concept in almost every programming language, right? And so basically, I'll be explaining how importance of queues, how we use them, why we use them, and in a later stream, we would also look at like the uh, implementation of queue, right? Why would we want to implement a queue in the first place? So for today's session, we'll go into queues like I've said before in Rust. So first of all, we'll learn how to do the implementation, um, how to implement like basic queue using the VecDeque, which is um, coming from the standard library. Then we'll build custom queue implementation from scratch, right? So we'll use one that's coming from the Rust library, then we'll build our own queue from scratch. Then we'll look at why we may want to build our own queue from scratch, and we'll also look at why we should use the VecDeque that was provided by the Rust standard library, right? So we look at all these things, and I hope everything goes well. So once again, I'll just give a quick recap, right? Um, so so a queue is basically a linear data structure that follows the FIFO principle. And what the FIFO principle means is that it follows the first in, first out, um, you know, principle. And what this means is that, for example, if you've ever been to like a bank or like you go to buy ice cream and you have to stand in the line, right? So the first person to join the queue will be the first person to leave the queue. So, you know, think of it like, going to a bank or going to buy a ticket for a football match, right? So the first person to join the line is the person that gets attended to first, right? So in our own implementation, we'll be looking at some common operations, enqueue and the dequeue, right? So the enqueue, what it does is that it adds elements to the back of the queue. So let's say on this line where we went to get ice cream, we have a couple of people on the line, and we want to add someone else to the line. We'll probably do that by you know enqueuing them to the queue, so adding them at the back of the line. Right? Then, if we want to serve the first person in the queue, we would have to dequeue them. That is, take them out from the beginning of the line. So, like I said before, Rust provides an efficient way to implement um, queues using the VecDeque collection, which comes from standard library. So we'll look at that and see how we can, do that implementation in our code. So without wasting much time, I would quickly start writing the code. So one thing to note is in our last stream, I used Rust C to build a binary. So you see the main binary file here and all that. So, but today's stream will be using Cargo because I really want to make this, whole stream more interesting and a little bit better compared to the other ones. So, without further ado, I will just start. So, we'll first of all implement the queue using the vector. Do this. All right. So, like I said, we have a queue that's already built into the Rust standard library. So the way we get that is we get it from the standard library. So say std, and in there we have collection. In our collection, we have vecDeque. Right. So now I'll take out the hello world. And the first thing we'll do is we want to create a new queue. So I want to create a queue. So we'll select let's call it a queue. QUEE, and it says equal to our vec. So vec q.new, right? So in our last stream, we talked about types and all that explicit type implementations. So here, instead of just leaving it empty this way, we are going to pass in a particular value. So the reason you're seeing an underscore there is that this kind of situation states that the queue can take anything at all, right? Any type, be a boolean, an integer, or a string. So yeah, I'll pass for this our case, we want an I32. I'll pass an I32 there. So with this, we've created a queue. So next we would push elements into the queue. So basically, we'll enqueue elements into the queue. And on the VecQueue itself, we have methods that we can call to do this. So we'll say elements. So we'll say queue dot pushback. So it's called the pushback, and we'll pass a couple of values in there. So I'll start with 5, and I will just copy this and duplicate it multiple times. So say 5, 10, 15, 20, 25. Right. So with this, we've added elements to our queue. So to test this, we'll go ahead and print. So let's do a print. We can see what we have done. So print. After queuing, and want a beautiful format, and then we'll pass our queue. Right. Pass our queue. Yeah. We'll save this and we'll write this first. then I'll go run. You can automatically see that we have, okay, I have to correct this. So it's supposed to be enqueuing, and I'll run this again. But you can automatically already see that we have 5, 10, 15, 20, and 52. Okay, 25 instead of 52. That's once again. All right. So we have something that is kind of like a vector in Rust. So it's kind of like an array if you're coming from a JavaScript background. And it contains all these elements. So this, um, in our case, is a queue. We've created a queue, right? So next, we are going to look at how we can like the queue elements in our queue. How we can, so the queuing basically means removing elements from the index, right? From the front, from the zero index of the queue. So from the front of the queue. So I'll add a comment here. I'll say um, the queue and element. So say if that's let's pass it here and say front. So that front. So we'll use q.pop front. So on the queue, there's another method called the pop front, and similar to the pushback that helps us to remove things from the queue, right? So we'll say q q q dot pop front. So in that place, would then we can then add another print statement. So without wasting much time, I'll just copy that and paste it here. And here I would say the queue. Take this out. Queue. And here I would pass in front, right? So I'll say front. Just take out this stuff. And then have a queue. Okay, so I'll run this again. So I'll go run. So you'd see that I would have 10, 15, and 5 would have gone out. Okay. Queued. What is happening? Front. Okay, yeah. So okay. Okay. Yeah. So what we can see here is that um, we've dequeued 5 from our queue, right? So if I go ahead and run the line of code on line 13 again after where we are doing our dequeuing, you should be able to see the queue without the element 5 in it, right? So I will give this a try and run it again. What's this? I'll go run. All right, so you can immediately see that the first part we had, the first print line statement on line 13 had the complete elements that we want. While the second line showed the element that we removed from the queue, which is on line 17. Then running that line of code again on line 20 now shows us a new updated queue where we no longer have the value of um, element 5 in it again, right? So in this case, we've been able to remove the we've been able to dequeue an element from the queue. So in the simplest form, right? What you have to take note of is the queue.pop forms, right? So we are then using an if statement, an iflet to do that check and print something to the terminal, right? So we can actually just do something like a let, something like this, and equate the q.pop front and just print whatever value we get to the console. So there are so many ways of doing this, right? So in the most simplest form, this is one way that I like to do it. So now we can also check the element that is in the front of the queue, right? So I will take this out, I'll comment this out. So we can check the front element. So if so here we still use the same format. So instead of writing everything, we can just paste it here, and then we can say so to get element that is in the front of our queue, instead of using pop front, we would use front, right? So that's another method that is on our queue that standard library provides for us, right? So we save this, and one trick in Rust, and you want to format your code, right? Kind of like the way Python works in JavaScript. There's something called cargo FMT. So you can run that, and you can automatically see how it's just did the formatting, especially for this line of code that was not arranged. So now, what we have here is basically very similar to what we had here. But in this case, the only difference in this case is that um, we have the front. And so I'll change this from the queue to front elements. I'll spell today. And I'll save, and I will just comment out this. Okay, I'll leave those so that we can be able to distinguish and see what is happening in the code. So I'll run this again. So I'll say cargo run. So you can automatically see that we have the first place where we printed all the elements in our queue. Have it here. So we have the dequeued element, the one that was removed. Now the one that is at the front is not 10, which we just printed to to the um, to the terminal. Right, so I'll clear this once again. Okay. All right. Now, the last one, but not the least, is to check if the queue is empty, right? So we can check if we have an empty queue. So add a comment there, say check for check the queue is empty. Exactly. I don't know why this is what's it for me. So it could be a very simple line of code, right? You don't have to do an if or whatever, right? Although we can still do that, but there is no need for doing that in this case. So here we can just print line, print line. We say queue is empty. So I'll say queue is empty dot is underscore empty. So that would tell us if our queue is empty or not. So this returns a boolean, right? It returns a boolean if it is true or false. Right. So when I run that code, I'll comment out the rest of this. Now we have a clean terminal to work with. So when I do cargo run, have false because our queue is not empty. So, but if I go ahead and I undo this and I um, like print this to um, um, four, and there are better ways of doing this. You can like write a while loop, and use it to do the mapping. But I'm lazy today. But let's just run this code again and see if we'll get through for finding out if the queue is empty. Run that a couple of times, I think 5 times, because we have 5 elements in our queue. If I run this, oh, it didn't work that way. So I have to write that loop to kind of, or I just have to repeat this particular if statement multiple times to do the pop front exactly. I don't know what I was doing this. So we have to do this like this. I have to call it multiple times. Save um, FNC to format the code. So let me see if it will take out 10 from the beginning. So I'll clear and I'll run again. I should have um, exactly. So now I now have 15 as the front element. It has removed 5 and 10 from the queue. So probably if I want to do this, I have to multiply this. I have to like duplicate it. That's not like the best way to do it because of this video. Just go ahead and do that. We can write a loop that is going to, call the three.dot a couple of times to remove all the elements in front of it. Do this and 1, 2, 3, 4, 5, save and format, and then run cargo run again. And we should now exactly so now we now have true, right, for this line of code. So it's telling us that our queue is empty, right? So so this is basically how we can implement a queue using Rust. So the VecDeque itself, right? So let me undo all this. So the VecDeque itself, what it does is that it makes implementing a queue, right? It makes it incredibly simple to achieve in Rust, right? So down the line we'll talk about look at the differences between the VecDeque and implementing it manually. So without further ado, I will go ahead and comment out everything here and start again from scratch. So comment everything and I will just quickly create another main function. So, function main, and in this place we have a simple hello world program. And so now we are back to scratch. So now we're going to take it a little step further. And like I said before, build our own implementation from scratch. One thing we'll be making use of here is the VEC, uh, like it's called the VEC or vector under the hood. Which we use it to hide the internal implementation of what we are going to do using a struct, right? So I know that might not make sense that much, but as I write the code and explain the entire process, it will begin to make sense how that works. So this is the plan. First of all, we'll create a struct that we'll call a queue, and we'll create that struct with a vec as an internal storage for it because a vec is like an array, but the only thing is that it can not take different um, um, you know value types or elements of different types. So it cannot take an integer and boolean. It can only take booleans or integers or floats, something like that, right? So first of all, we'll create a queue with a queue struct with a vec. So the vec is going to be our internal storage. Then we will then go on to manually define these methods that we had written in our previous implementation, right? Try to write methods for enqueuing, dequeuing, and picking. So picking is like looking at the front of the queue in of itself. So without rambling so much, I'll just go ahead and start writing the code. So the first thing we are going to do is to write queue. And later on in our streams, I will also talk about structs, but not struct. I will talk about generics. But in this code, I will just, in today's stream, I'll just touch a little bit on it. I wouldn't really explain much on it because we would have a whole lot of streams that is going to really talk about generics in Rust. So in case you see the capital letter T, weird capital letter T that is between angle brackets, and just know that they are like placeholder text that can replace any type of values, right? Kind of how it works in other strongly typed languages. If you're familiar with them. So now, first off, I have to play our structure. So the struct is the same thing as structure. I'll say struct, and like I said, we're going to call it Q. Uh, yeah, I'll just call it Q, and it's going to be a generic, like I said. So I'm not going to go much into explaining that. And it's going to have a key value pair of data, and that data is going to, embody a vec, and in that vec, we are now also going to pass values to it. So we also pass our generic type, which is the T in there. Right? So this is our key. Then we also look at implementations, which is something we'll talk about later on. So, but we'll write an implementation of on our queue, right? So we'll say I am here. All right. So this is more very similar to object-oriented programming if you're familiar with the concept. So you can read more on that. And so here, this is also a generic implementation. So we pass T. The reason I'm using T is because it is a convention in us. Right? It's not like there's any set out rule. I can use anything. I could change this to A, right, and it will still work. Right? So it's not like it must be T, but it's just that that's the convention. So this implementation, we'll call it Q, UUE, and we also pass the generic again. And yeah, so the first thing we want to do, similar to our previous implementation, so I'll just comment this in again, so we can always go back to it. So the first thing we want to do is we want to create a queue. Right? To create a, we want to do something like this, but this time around we're going to do it manually, right? So we'll say, with this comment, create a new queue. So we'll come here in our implementation block, say create a new queue. Okay, so to do that, we'll use a function. So we'll call that function fn new, and this function is going to return self, capital letter S, return self, and then we are now going to call our struct. So this is q u e u e, and in there we have our data. So the data. So if you take a look at what we defined here, the q, which is this data, and the vector, right? So we're now going to call, and I'm going to do vec, dot new. So new, so we're going to call this method. So this is how we are going to do it. So with this, we've created a new um, a new vector. So don't mind this error we are seeing here, is because we have two instances of the main function. So that's why. So with time I'll take that out, and it would we'll no longer see that error longer. So now that we've created an instance that's going to enable us to, I've created a function that's going to enable us to instantiate a queue. Let's go ahead and write a function to do our enqueuing. Right. So I will once again copy this. I'll paste this here. I'll paste this here. So now we're going to write a function, and that function we'll call it enqueue. Right. So we'll say fn, similar to how we did this. So we'll say enqueue, and it's going to take reference to itself, which is going to be mutable, and it's also going to take it's going to take data. So it's going to take something. In this case, it's going to take T, which is data or item, because in Q, what it does is it adds elements to the back of the queue, right? So it has to take something. I would say this. Um, so here we have a reference to new self, SLF. So this self is referring to the queue structure, right? We can read more on this. So we'll call these elements, or just call it E, and we'll set it as T, right? So we've done that. The next thing we're going to do, we're now going to use the self. So we want to, on the vec, right? On the vec, we have a method called push. So what this push does is it works kind of like similar to JavaScript. And I do a lot of reference to JavaScript, yes, because I have a lot of background in JavaScript. So it's just like, how you have array methods, you have the pop, you have the push method. So it's similar to this, right? The vector. Here we'll use self, and self in this case is referring to the queue itself. And we know that the queue is an implementation, right, on the vector itself, right, on the vector. So what we would say here is we'll say self dot data. So you can already see that it's already suggesting that self dot data dot push. So we have, right. So if we try to, let me see if VS Code is going to, so push E. So you can already see that it says appends an element to the back of the collection. Right? This is like an explanation from my, I think this is tab 9 on VS Code. It explains what is happening here. So we have vec.push, and we are passing 3 into this. It's going to update the one that. So this is just like an example. So that's what's happening here. So in this case, what we are passing into this place is E, which is the element, right? So with this, we've automatically created a function that would help us to enqueue elements in our queue. So the next one we are going to do now is we are going to then go ahead to do the dequeue, right? So I'll just copy this. So dequeue element for the queue. So also write the function. So it's still a function. Say the queue capital letter FN. Okay. So in this place, I would also take a mutable value. I'll take myself, like I'll take self, which self is like I mentioned before, struct. But dequeuing doesn't require any data because what we are doing is we are removing stuff from the vector or from the array, right? We are removing, so we are not going to accept any value. So I will just reference the mutable self. So the reason everything has to do with referencing and mutability has to do with the concept of borrowing and ownership in Rust, which is another big conversation altogether, right? But that's not the purpose um, of this stream. So we just focus on this. So moving forward, we'll return option. So the reason I'm returning an option is because it helps, with error handling, right? So an option is an enum. So you can actually look that up. Use an option, and it's also going to be a generic pass in it. And then we'll say if, right, if self dot data. Remember, self I said is the struct. So if self dot data, uh, oh, I don't. If self dot data is not empty, right? So if it is empty, sorry, we don't want to do anything. So if it's empty, we don't want to do anything. So we'll just return none, right? Else, so else we'll now use the sum. So we'll use sum to remove value from the front of our what's it called? The front of our queue. So in this case, I'll use sum. And we know we want to always remove the value that is at the front, and that value at the front is going to always have an index of 0. So we say inside our sum, we say self.data, and there is a method called remove that the vector uses. So we remove, and then we pass the index. So it's already suggesting the index. And if you look at this, you see there's already examples of how to remove, right? So we'll just pass the index. And the index in this case, which we want to always remove when we call the queue, is the first element. So the first guy on the queue is the person that we want to attend to, right? So like I explained earlier on, this is kind of like the banking system, or you went to buy an ice cream, and it is based on the first come first served basis, right? So that's what the DQ does here. So we pass the index of 0 because we know we want to always remove not 0, we want to always remove the element. So what this line, what it does for us is it removes the first element, right, from queue from the queue. Right. So that is that for dequeuing. You can already begin to see how easy, and this is just a couple of concepts that I've just glossed over, which are really simple concepts that would later on. So the next function we are going to work on is the peak. So the one that shows us the elements at the front of our queue. So we'll just copy that comment once again. Front element. So what we are doing here is we are manually writing everything that we did automatically from the VecDeque that we got from our standard library, right? So the pop front, we rewrote it. Front, we rewrote it. The pushback, we rewrote it. Right? So I'm rewriting everything manually this time around. So here, I'll add that comment and check front. So here we are going to write the function, and we'll call this function each FN week, and it is not going to be mutable. Take a reference to itself, and we'll return also return option because of error handling. Return an option. That option will take a reference to T, and then we want to return self dot data dot data dot first. So first is another distance. So it returns the first element in the vector, right? In our vector. So if you look at the explanation again coming from my type 9, helps a lot. Um, kind of shows us the first element in our vector. Right? So you can do v dots. That's exactly what uh, I'm doing here. Okay, so with this, right, we've done almost everything. Remaining the last one, which is implementing the function that checks if the queue is actually empty, right? So if you remember when I explained with the inbuilt VecDeque, I used this particular line to check, which is vec dot is underscore empty, to check if it is empty, right? So we're going to also write that function manually, right? So I'll do that here. So I will just take out this particular first function that we did, first implementation, so I will not be seeing those errors again. Then, okay, so all these ones are warnings because we've not use them. And guys, this one thing about Rust is that Rust is not just type safe. That is not the best. In my opinion, that is not the best um, feature of Rust. For me, I strongly believe that one of the best features of the language is the error messages, right? The error messages are amazing, right? It's amazing. You will not believe how helpful the compiler, does and helps one when writing code. So, guys, please confirm if you can hear me. Please, if you can hear me, leave a comment in the comment section. Guys, confirm if you can hear me. Okay, so I guess I will just continue. I don't know if you guys can hear me. Um, guys, can you hear me? Hello, crap. Okay, so I'll just continue. Um, okay, having a little bit of a glitch. I don't know what's happening. Hmm. Okay, guys, please confirm if you can hear me. If you can hear me, please leave a comment in the comment box. Thank you. Um, Having a bit of a lag. I don't know what is happening. Please confirm if you can hear me. If you can hear me, leave a comment. Anyways, I'll just continue. So next, we are going to implement a function for, you know, emptying the array, emptying the queue, right? So I don't know what is happening. What is happening? Okay. Oh, okay. Oh, thank you. Okay, thank you. So having a bit of a network issue. So the final function that we're going to implement would be the function that checks if the vector is actually empty. So say fn is underscore empty, and we'll take a reference again once again to self, and we'll return a boolean because this in the original function returned only true or false. So we'll say self dot data. So very similar to the is empty that we had. It's the same like method with the one we had in the queue, right? So we'll say data dot is empty, and that should be pretty much it, right? So with this, we have implemented all the functions that manually that we got for free from the vector, the VecDeque, from the VecDeque that the standard library gave us, right? So in order to do this, we'll then first of all create a queue in our main function, right? So in our main function, we'll create a queue, very similar to how we did it before, but this time we'll just say let's mute be equal to, okay, let's mute have a queue. Let's call it queue and say queue.new, right? So we are calling this function. We can just leave it tap this twice, so we'll leave it empty, like with an underscore to specify that it either takes can take any type, right? It can take a boolean, can take an integer, can take anything whatsoever. So we'll go over to, so now we are using our new function, right? We're using this function. I'll save. Let me see. Exactly. So the error should disappear now for this. Then next would what's happening? Q.new type annotation needed to, oh, okay, I need to infer the type. And why is that the case? Why is that the case? Why is that the case? Type annotation. Consider specifying the generic. Okay. Type annotation type parameter T declared as a struct Q. Consider specifying the generic arguments. I see. Okay, let me see. I pass an I32 here. What would happen? Okay, take this out. Save. Oh, I see. Okay, so I just needed to pass the type. So I'm expecting integers, and I just did that, and that error has gone. So what you're seeing here is just warning saying that we've not used this variable. So variable, if this is intentional, prefix underscore whatever, just to, so we can just prefix an underscore at the beginning of this to escape that error. And if we save, we should not have that error any longer. And we can do the same for the rest of the functions, but we're going to use them in a bit. So without wasting much time, and this stream is already getting too long, I will just go ahead and add elements to the queue. So I'll say queue. So remove the underscore because I want to use it. So I'll say queue dot, so the function which is enqueue, right, which I created initially, I'll say enqueue, and I'll pass a value. So I'll pass 1 here, and copy, paste. I'll do cargo fmt to format. Okay, I didn't save that. Overwrite. Then once again, format everything, and I'll change these values from 1 to 2 to 3 and to 4. Okay, so I've added elements to the queue. So instead of typing again, I'll just quickly copy what I had from here and use it in the old code. So paste this. So basically, I want to print to the command line, right? So I will say queue.data, right? So queue.data. So it's going to tell me the element I've added to the queue. right? So so when I run this, clear, and run it again. Okay, so we have a lot of warnings. So we have those elements 1, 2, 3, 4, 5, 1, 2, 3, 4 in our queue, right? Then we'll go ahead to use the deque function. So it's very similar to what we had before. So if let's sum. So if let's sum, we'll pass front. So what's the value of front? Call it front variable, and we'll say q. So instead of calling front this time around, we'll say deque. Sorry, is it pop front? It's pop front. Yes, pop front. Instead of doing that, we'll say deque, right? Because that's the function that we had implemented manually. Say deque, and then we'll print some things here. So we just, instead of writing that from scratch, copy it and paste. So we have this. Okay. Delete this. Weird. I'll just write it manually. Print line, and I'll say q dequed. Exactly. Then I'll save this, and I should, instead of having 1, 2, 3, 4, I should have 2, 3, 4 when I run this. So I'll go run. Yeah, so I now have 1. So that means 1 has been removed from there. So if I do similar to what I did before, if I run this here, save, and I run again. Exactly. So I should have 2, 3, 4, and then it's showing that I dequeued this from the queue. So the next, I'm now going to go ahead and do a pick and then check if it is empty, right? So next, I'm going to similar to what we did before. So just an if let, with sum and all that. So say if let's, so sum past front. So instead of dequeuing, I'll pick, because that's the function that we wrote. So the pick function is then going to tell us the first element that is in our queue. So I'll copy this over, paste it here, and I'll call it queue picked. And then yeah, basically that should work. So I'll just do it like this. Clear the terminal, run it again. Exactly. So the first element is 2, right? Because that's we've dequeued 1 from the array, and so the first element we are picking at this moment is 2. So the last but not the least is the one that then returns the boolean, right? The value, the true or false, which is empty, which we had had the privilege of getting it out of the box from the VecDeque that comes from the standard library here at the top. So using that function, we'll just do a straight print line. So we'll do a print line, and in that print line we say check is empty, and so we'll have something like this. So we'll just say queue is empty, right? So we'll just call the queue dot is empty, and if we run this, we should get false. So cargo run should get false because it is not empty. Exactly. So we have this here in this place that says it is not empty. So you guys might be wondering what is the difference between okay, but first of all, the key observation, right, is that the VecDeque, which is the deque which we get from Rust, is easier to implement, right? It makes everything very easy for us. So in while using vector and having to write it manually comes with a lot of code and manual tweaking of things, as you can see that we did here. So we had to manually write a function to enqueue. That's to add elements at the back of the queue. Functions to remove elements from the starting of the queue, at the front of the queue, element to pick at the queue, and sorry, not elements, sorry, functions. Sorry, function to check if it is empty, right? So um, between the VecDeque, with the Vec and the VecDeque is more efficient for implementing queuing rust, right? And then the reason for this is because a Vec is a growable array that supports efficient addition and removal of elements at the end, really at the end of the Vec, right? It takes a time complexity of O1. However, adding or removing elements from the front is not efficient. It's not efficient. And it does that in an O of n time complexity because it requires us to shift the remaining elements. So when we remove one from the starting, we have to shift others, right? So um, a vec queue, right, is on the other hand is a double-ended queue, right? So um, it implements a ring buffer. So a ring buffer is a more advanced. It implements a ring buffer. It efficiently supports adding and removing of elements from both the end and front of of the queue in an O of one at a time, right? So enqueuing, when we use VecDeque, has an O of one, while dequeuing has an O of zero. So basically, in conclusion, we use Vec DQ for better performance and flexibility, since it avoids the costly shifting of elements that occurs when we use a vector, a Vec, when dequeuing from the front. So we can also use a Vec only if we want to dequeue from the back, right? So like in a situation whereby we are implementing a stack, so we can use a Vec in that case. So guys, thank you so much for joining me on this one. Series of and I don't know, but thank you so much for joining me on this. And I would see you